Hello, today we continue with you to solve problems on the application of Newton's laws and the types of forces that are involved in acting on the same body. Let's get started. Some friends decided to go for a ride in a hot air balloon. One of them was late, and when his friends got into the balloon, the total mass of the basket friends was a total of 1,220 kilograms, and the balloon had zero buoyancy. When the late friend got into the basket, the balloon began to descend downward with an acceleration of 0.56 hundredths of a meter per second squared. What was the mass of the tardy passenger? In this case, you and I are going to look for the mass of the late passenger, and we will denote it as m1. And what do we know? It is known that the total mass of the friends who had time to sit in the basket and the total mass of the basket was 1,220 kilograms. At this mass, the balloon has zero buoyancy. That is, it is in a suspended state. That is, it does not go up and does not fall down and can be at any height relative to the ground. For the last passenger, apparently there is a possibility to get into this balloon from some platform. When the late friend got into the basket, the balloon began to descend with an acceleration of 0.56 hundredths of a meter per second squared. Meters per second squared. Actually, why did this happen? When we talk about the fact that the total weight became greater, then of course the equilibrium between the forces that act on this system was broken, and apparently the total weight began to exceed the force that creates the lift of this ball, and therefore this acceleration appeared. Let us make two constructions. The first for the situation when there was still zero buoyancy, and the second when the acceleration of this system has already appeared. So let's draw the balloon in this way when it was in equilibrium. Here is the total weight of this system, which we'll denote as W. Given the index 2, let's write it as W2 to refer specifically to mass 2. And here on the balloon itself, let's put another force, which will indicate that this balloon is trying to fly upwards, but gravity is preventing it from doing so. Given that there is no acceleration here, that is, the balance is observed in terms of zero acceleration, we can say that these two forces are equal to each other in this case. And if we decompose the total weight of the basket and the people through their masses, we get m2g. What happens next? Now we've got the balloon itself getting heavier. So now we've got the weight of the late person in the basket. The weight of the latecomer and the basket of people that were together before. This is the common vector. And here we still have the same lifting force because nothing has changed for the balloon as a whole in terms of interaction with the air. And let us make this vector a little bit bigger, even add one more vector, taking into account that now there are two gravity forces of two objects. And there's a certain amount of acceleration that's going downwards in this situation. What do we do now that we've got the accelerated motion of this body? We of course apply Newton's second law in terms of the acceleration that has appeared. The total mass of the given objects, that is this m1 plus m2 times the given acceleration, that's the sum of the forces acting in the direction of acceleration. In the direction of acceleration, we have the force of gravity of the given objects. We will write it as W1 plus W2 and minus the lifting force for this ball. And now our task is to write down everything that we have here. Let us now start writing from here and show that m1 plus m2 times a is. Now what is the weight of the first passenger? It is the product of its mass by the acceleration of free fall. What is the force of gravity acting on the balloon as its passengers sat there until the last passenger arrived? It is actually, as we see, the very force that keeps the balloon afloat. So we can substitute for W2 the value of that force. and minus the F that appears in this equation. After such substitutions, we see that the two given forces cancel each other out and we are left with this expression. From here we must find M1. To do this, we open the brackets. M1A plus M2A is M1G and groups the unknown masses on the same side of the equation. Then we get M1A minus M1G is minus M2A. Here we can take M1 out of the bracket and then we get M1 times the minus G. Here we get minus M2A. And then we write down the final formula, and here the minus sign, we immediately multiply the whole equation by minus 1, and in the parenthesis we have the two expressions swapped. It turns out then M2A divided by G minus A. It remains only to put the number of values in this formula. So M2 is 1,220 kilograms multiplied by an acceleration of 0.56 hundredths and divided by the difference between the acceleration of free fall and the acceleration of this ball. So, after calculations with an accuracy of 2 digits after Tsapitoy, we get the answer 7486 kilograms. Well, taking into account the incoming data, we have the right to put 2 digits after Tsapitoy. So, in this way, the actions of gravity together with the actions of other forces can lead to the calculation of such problems and show how it is possible to create buoyancy in the air. Here we can say that this force is called Archimedes' force and it acts not only in air but also in liquids. We will work with this phenomenon a little later. So that's the end of the task. See you in our next lessons. Goodbye.